Okay, good morning, everybody. Let's go ahead and get started. Thank you all for coming today. Welcome back to another Build Informing series. Today we are talking about passive cooling. I won't blab on too much about this right now, but if this is your first time you're hearing about this concept of passive cooling or overheating, I want to warn you, this will certainly not be the last time you'll hear about this. This will be an ongoing topic all over BC and really the globe. So if you're here today, which you are, you're one step ahead of the curve. You're a little bit ahead of your competition here by breaking through into this really interesting topic. Today's event is brought to you by the Township of Lang Green Buildings team, and there's Sarah Maleska on our phone here. We have Jean Surendran, a technical building specialist, and as well as myself, Green Buildings Manager, Kevin Ramlew, and Monty Paulson, our speaker today of RDH Building Science, an excellent speaker, a real body of knowledge on many topics, including passive cooling. So we're really happy to have here today with us. And last but not least, BC Hydro, thank you for your ongoing support for all of our, or many of our events. We very much appreciate that and anticipate an ongoing relationship. And our accreditation bodies, you see there on the right, ABC and OABC, BC Housing, etc. Let's move on. Okay, so our agenda today is, so I'll have a few updates and a little bit of stuff about what's going on out there in the market. I'll then hand it over to Jean Surendran, who'll give us our compliance corner notes and maybe a little bit of a preface to today's topic. Next will be Sarah Maleska with our survey recap of our last event and we want to share what you told us, what your thoughts and concerns are around our previous topic around Windows administration and some interesting polling. Monty will then bring us the meat of the presentation on passive cooling, and then we'll close out and share some notes for next time. Okay, so just a bit of a recap where we were last time. So last event in March, we were talking about fenestration and step code. And to kind of summarize it, at least into one very small little piece here, better windows have a very big impact, or windows have a very big impact on your building energy performance. So an easy way to look at this, if you're playing with dials and depending on what your step code requirement is, here in the township, it's at 2 and 3. Better windows can either mean you can have a larger window to wall ratio, or better windows in the same window wall ratio will allow you for better building performance. So consider this as another tool in your toolbox in how you want to cost out your building, or what components you want to have for your building, and still while meeting the step code. And the example here has two buildings, one with 40% window to wall ratio and one with 55% window to wall ratio, however, with a slightly different window components, but otherwise roughly the exact same building performance or building energy performance. Updates to bring to you. Some big news here from the federal government. This first one I won't belabor too much, but this is a big chunk of change out there for the energy advisor community and programs. The federal government really wants to develop an industry for energy advisors, many more energy advisors out around the country. So there's about $10 million out there, and the federal government is looking for organizations, companies, etc., that can support the transition or the training, the development of new energy advisors out there in the market. So if this sounds like somebody or a company that you work for or that you have, take a look at this program. You can Google 10 millions for energy advisor, and you'll find all the awesome details out there. The proposals call is very soon, so you do want to start looking at this sooner than later. Something relevant to many people on the call here is also there's a very big chunk of change out there for retrofits regarding energy improvements. It's about $2.6 billion. There's about up to $5,600 per home for energy evaluations and retrofits over the next 7 years. There's a few examples of retrofits that exist out there or that are funded. So if this is something that you do work on or you do retrofits out there, review the program, and you really would be wise to start promoting it out to your customers and the public. We also will be promoting this. Oh, and if you had done any work as late as December 1st, 2020, there are retroactive incentives available. So the Clean BC is supporting also retrofits around the province. And the last time we met and the last time, we discussed a little bit about these programs and about kind of really the scale of money that's out there for new construction. My mistake. This is a new construction program. There's a fair amount of change out there for achieving higher steps in new construction. The last time we met, we talked about single family, an example of a single family home if you built a step 5 and with an all electric system. Today, let's talk a little bit about what happens if you are building a townhouse to the upper steps. So if you choose to build a townhouse to step 5, you are eligible for $10,000 per unit. Also about $1,000 for energy advisor support. And if this is an all electric building, it means zero gas or propane running to the unit. And this is an option. You do not have to take this, but if you do, you're eligible for an extra $4,000 on top of that. So let's see what that means out in a real project. This is a semi-real project. ABC Builders are building a townhouse complex in the township. They have 6 buildings with 5 units each. That's about 30 in total. They want to dip their toes in the water and try out step 5, a little bit of research and development. So they choose 2 buildings, 5 units each, to build a step 5, to learn, to go through the process to see what does it take. Ultimately, they're doing research and development to stay competitive out there in this very, very dynamic construction industry. So we compare or we reference the Clean BC the rebates, and we see that at step 5, you get $10,000 per unit, and you get energy advisor rebate. And for 2 buildings at 5 units each, you'll be eligible for $111,000. If you choose to have the all-electric bonus and 0 gas lines, propane or natural gas to each unit, you're eligible for $4,000 each. Extra amounting to $151,000 for the 2 buildings. The Township of Langley also has some rebates available, and you add that all together, and it's roughly about $6,700. So if you took advantage of the Clean BC and Township programs in your development for those 2 buildings, roughly, or for 10 buildings, you're looking at about roughly $156,000. Now, I won't stay on this for too long, but when we compare to the Step Code Metrics report that does a huge amount of costing analysis to reach Step Code, and it really depends, I acknowledge it depends on many different situations, what we're seeing is the amount of money that's being released out there today is very substantial. It can cover the entire overcost to get to Step 5 per unit. So this is something you really, really want to look into. Step 5 is coming, it's coming everywhere around the province and eventually the township, and net zero energy ready will be a federal requirement by 2032. So it's probably wiser to start looking at this today than tomorrow to prepare. And for further questions on this program, you can check out Clean BC Better Homes or as well reach out to us. Something very exciting, it's something we're keen on, and I'm sure you are as well, is air tightness in buildings. This is a major component to energy performance and meeting the Step Code energy performance targets, but also in Part 9 are air tightness requirements. So we've hired and partnered with UBC to hire a UBC scholar who's a research professional. For us, it's Ezgi, an architect. And a little bit of background of this. So Step Code for Part 9 requires increased air tightness requirements as you go up in step. And as we go from today, for example, Step 2, 3, which is roughly 3 air changes or 2.5, all the way to Step 5, which is 1 air change per hour, or otherwise a 67% reduction. I have Passive House here as well. If those who want to try that out, that's a 80% reduction. That's a significant reduction or otherwise improvement from today's practice. It's very important to acknowledge that higher steps or higher air change requirements, there's a lot more attention to detail, and that also means there's a lot more opportunity for error. So we acknowledge that this is coming down the pipeline and a requirement. So what we're looking to is our scholar to look at the major building envelope and air barrier components and to start looking about what the best practices are. If you do A, B, C, and D, you will, for example, have an excellent air barrier. Look at all those best practices and then simply, well, not simply, but ask the question to industry, who's doing what? Are you doing this best practice? If not, then who's doing it? And are we doing a little bit of this? Oh, I thought it was this one. So if that's the case, this is what this report aims to do. It just aims to simply identify what is the lay of the land, what are we doing, what are we not doing as a collective whole, as in entire building industry who are relevant to the building envelope and air barrier. So we'll be doing a research, we're identifying those major components, we're asking out the industry, and this is actually also a call for help. We do need your help on this for many of you on the call. We want to ask you who's doing what, and we're not pointing fingers at anybody whatsoever. It's simply, what are we doing and what are we not doing? This tool is going to be given back to industry to say, this is what we found, and we'll leave the rest to you to start identifying, okay, how can we start addressing this? So if you do work in the industry that, or any industry that does overlap with the building envelope or air barrier, you will likely be contacted either directly through us or through an association. So please, we're asking for your help to conduct the survey, provide your feedback. It's much appreciated, and you will have access to the tool or the results in the end. This bullet's important. The more participation, the more accurate the data that we're going to gather. And I'll highlight our next Builder Forum series, which will be happening in September. It's on airtight buildings, very, very similar, close to the topic we were just talking about. So airtightness, as noted, is a major factor in energy performance. And I don't think I need to speak any much more about that, but we'll be talking about that in September. So please look out for that. I'm going to hand it over to Ajeen for the compliance corner. Thank you.
Thank you, Kevin. Good morning, everyone. Sarah, can you make me the presenter? Yeah. Right. So can everybody see my screen? Yeah. Okay, so I just wanted to give some updates on energy modeling results, especially like focusing on the energy results. So yeah, so this is mainly some notes for the energy advisor and the energy modelers. Like you should be able to, like when you do an energy model, you should be able to understand and interpret the results. So we have been having some cases like, it's a very less response from the energy advisors. So if you see like some results does not make sense, I mean, you have to review it thoroughly and understand why that results are not making sense, or maybe it's like kind of different. So the reason is like, sometimes the results might be right. For example, we had a project where the teddy was too low. So it could be the geometry of the building, it could be the mechanical controls, or it could be the windows or something, like we don't know, like, right? Or maybe it could be an input error. So we just want to, like, it should be the responsibility of the energy modeler or the energy advisor to interpret the reason to the HJ. We had some of the examples that I'd like to list down is like really low TEDI, MUI, or TUI for a typical design practice, which typically we don't expect, right? And also sometimes you might have really high GHGI for heat pumps, for a building that's with heat pumps and as only a backup furnace. That could be the control settings in the modeling software. So yeah, that's one update what we have for energy advisors and energy modelers. Uh, I'd also like to give a brief on why we chose passive cooling today. So we all agree, and like we all agree, climate change is real. So it is getting warmer and we all can feel it, right? So that's one of the main reason. And then overheating is already a concern today, and it's going to be just really bad in the future. So we need to prepare for that. Now, it should be easy for a design team to have an air conditioner in there and say, okay, we're done with it. That's it. So we don't need to do any passive measures. But like a passive measures can have a bigger impact today, and even like it might be helpful for to reduce the size of your mechanical equipment or reduce the occupant energy bills, which is what I will be concerned as a user. So the message here is plan and design for the future so that like the buildings are going to be there for a longer time. Now, some notes for the energy advisors, specifically for the Part 9 world. Yes, at this moment, we don't have a regulation for Part 9. BC Building Code does not say anything about overheating in Part 9 buildings, but it could be because HOT 2000 does not have the ability to model overheating hours. And also, there's enough cross-flow ventilation in a single family home or even in townhouses so that uh, you don't need overheating analysis. So that could be the reason, but I don't know. Uh, but energy advisors can actually play a bigger role. We are actually talking about best practices here more than like something that's required. So you should, I mean, it's a good idea, like as an energy advisor, if you can consider a very balanced approach of like meeting the step code requirements and then also thinking about the overheating reduction. So that will be like, it's basically at the end of the day, you're making a better product and your clients or like your tenants or the occupants are going to be happy about that. Like for example, I would like to just share one example here. Like I've received some projects where the TEDI is like so low, but they're still using a solar heat gain coefficient for the windows of zero point 0.4, and this is for single family homes. So there is an opportunity here to reduce that heat gain. So you can really think about it when you're doing a model. Now for part 3, there is requirement for building a passive cooling measures like as per City of Vancouver modeling guidelines. There is a 200-hour overheating limit, but then if your building is having a air conditioner, you don't need to do that. So, but if as a developer or as an architect, like if you can hire an energy modeler way ahead in during the design stage, a modeler would be able to test out different strategies, like okay, how long the shade should be, or maybe what should be the window size, or like what should be the window solar heat gain coefficient, things like that. I mean, they can test it out, right? So it's very important to get the modelers as soon as possible on the design stage. Uh, Also, like the modelers can consider future weather files for simulations because their softwares can do that. So, and this will help help inform the design team to to make changes to their design according to the output of the modeling results. So I'm just going to show you like if anybody is interested. So there is no requirement at the moment. So, but if anybody's interested in testing out some future weather simulations, we have done a little bit of homework for you. So as you can see, like as per Vancouver modeling guidelines, you have 80% acceptability limits for as per ASHRAE 55. So for Abbotsford weather file, which is what we require as a municipality, this, as you see on this 2016 column, that's the one which we are currently using. As you if you're a modeler and you're familiar with these numbers, you can see it's not really very different from what you have in City of Vancouver modeling guidelines. But then when you go to 2050, there is some degree of change, like at least it's very close to 1 degree average temperature change. So that's pretty big. And also just look at that. I mean, you have to also do an analysis for October to now, so which means a longer period of time. If anybody's interested in doing this, you can go to like, this. This is the link. You can go there, or maybe just Google Peakic weather files, and you can find the weather file. You can, I mean, we are using RCP 8.5, which is emission scenario, which I'm not going to get into details, but like you can download all the different options here. You have the different weather files. Try it out, download it, try it out, test it out. If you have any questions, you can feel free to reach out to us. One last slide on the same topic. We do have some developers trying out trying out or like preparing. They're preparing for the future regulations that's coming in, and so we had a design team for a project in Langley who voluntarily uh, simulated for future weather simulations, and they took measures. We were very happy. There was like, there's no hard requirements here, but they still opted to do that. And I'd like to share those results with them, with you all. So like in the first case, like 2016, which is a step code building based on a step code requirement building. So initially they had 187 hours of unmet hours, but this also included a solar Huygens coefficient of 0.28. Uh, but then when they simulated for 2050, the result was like it's like doubled. So now they did some measures. They included, they did not went really hard on it, but they updated the windows to have 0.22 of solar heat gain coefficient, and they also increased they changed the size of their HRVs, made it bigger so that more airflow can happen, and also included bypass valves. So that was actually a big upgrade from what they initially planned for. So based on that combined update, the update was like 142 hours. So from 187, it came down to 142, which is pretty good. So and they did just look for some very basic measures. So yeah, I just want to share this with you too. So that's it from me. I'm going to hand it over to Sarah to take over from here.
Thanks, Jean.
Yeah.
Start sharing the screen and hopefully it shares the right one. Okay. Can you guys see my screen okay? Excellent. Okay, so this is a summary of our survey that we sent to you all from our March 23rd Builder Forum series. I'll just quickly go over some of the highlights. So we especially like reading your comments, get more detail. So this comment here, the knowledge that Michael from Cascadia had about Windows was amazing. I was not aware of the upgrades available. As a restoration contractor, I'm usually focused on meeting code, not shooting for higher steps. So we love to hear that. Thank you for your comment. Someone else noted what they learned. So triple glass is becoming a more obvious way, or triple pane glass is becoming a more obvious way to achieve high performance. They are 50% heavier because they have more glass. They cost premium over double pane glass is about 10 to 15%, and the performance is double. Some constructive feedback, add the contact details of all speakers. So we added that at the end of the presentation. More pictures and slides and more built examples. Monty has a lot of pictures, which is a big bonus of his presentations. And also the host should wear a headset, so I changed my headphones this time, so hopefully it's working better for you all. And then what we also like to see is this bottom right one has the webinar increased your confidence in building to the upper steps of the step code. And so 55% said increased a bit, 33% said increased greatly, and 12% said stayed the same. So eventually, as we continue hosting these Builder Forum series, we hope that no one will be learning anything new and we're all experts. So actually seeing the state the same is hopefully people that know a lot. Okay, next slide. So now it is the Mentimeter time. So this will give live polling results and it gives a pretty cool visualization. So if you go to menti.com and enter the code 21610346, I will stop sharing my screen. Oops, sorry. I think I'm sharing the screen, so move that up there. Present. So yeah, that code, menti.com, code 21610346. Can you guys see my screen okay with the Menti? Oh.
Yeah, and for those on the call there, you can see the number there. It's just right at the top of the screen as well. It's a bit small, but it's right there. Sarah's hovering it there. That's helpful for me.
21610346. So this is a bit of a warm-up question. I love it when people put in all of this. Makes me laugh how different people interpret the questions. Working from home, WFH. Lots of Langley. bit of Surrey, some good representation from the Lower Mainland. We have 18 so far. I think we have about 110 participants today. So I'll wait a little bit. Sunny Township. Yeah, beautiful day today. Definitely a day where you want passive cooling in your apartment building or your home. Oh, Squamish, UBC. That's really great. Someone wrote in the chat, Surrey. Keep your participating. Great. I will move on and let's give it 15 seconds. And then we should be right on time. Yeah, Langley, it shows the biggest answer and the biggest font. And then we have Surrey, Vancouver, Abbotsford, the usual suspects. Awesome. Okay, next question. Oh, people are already answering ahead. That's good to see. So which of the following are passive cooling features? So this may feel like a test, but kind of is a test, but it's just for us to see where everyone's at for the presentation. So we have a tree providing shade for a building, a ceiling fan, a window air conditioning unit, window blinds, window shutters, low solar heat gain windows, and leaving your freezer door open. Great. This is very interesting. And we have all of these results, so Mentimeter results from past Builder Forum series on tol.ca/gblearn. And you can scroll down and there's a Builder Forum series section. And we also have our recordings and our slides, and those should be up for this webinar within about a week. And we also have question and answers from last webinars as well that we put in there. Great, we have like 39 participants. A tree providing shade for a building, low solar heat gain windows, window shutters, window blinds, ceiling fan, window AC unit, and then one for leaving your freezer door open. Thank you for choosing. Okay, I'll go to the next one. I'm guessing people have probably already answered. Oh, okay. Is passive cooling required for new buildings in the township of Langley? Select one. Awesome. The results are coming in. We have one person doesn't know, 3 people who say it depends, 5 people say yes, and 25 people say no. So this is very interesting for us to see. We have 37. I'll wait until the 39 people have submitted. Or maybe I'll just say now. So the answer is it depends. Everyone's favorite answer. So we have our greenhouse gas development permit area, and there's guidelines in there that they just talk about passive cooling, so it depends, which is everyone's favorite answer. No, lots of people say no. Okay, one more question. We're at 9:31. And then this one is related to what Ajeen was talking about. You mentioned maybe you kind of gave away the answer a little bit. So when is the best time to hire an energy modeler for your building? So this is a ranking question. So we have concept stage, development permit / schematic stage, 1 week before building permit, during construction, and never hire an energy modeler. No good. They're great. So we have 9 people. The results are not showing up, so maybe we'll just take a second and try to put this on. I'll wait a couple seconds before testing it out. That's too bad. Let's see. It'll keep on, I think it'll stay open for you guys. I'm just gonna see what's going on here. Either way, I'll be able to share it with you. Oh, there we go. So concept stage, it's probably very tiny on your screens. Concept stage is first, development permit / schematic stage is second, third is 1 week before BP, fourth is during construction, fifth is never. We have 37 people. That's about as many as I expected. So I will stop sharing my screen and pass the presenter over to Monty. Or Kevin, do you want to introduce Monty first, or do you think we should just go ahead?
Yeah, I'll just say a quick hello. Yeah, so so we're ready to get to Monty. So Monty Paulson is a amongst many things a passive house consultant. He is an excellent speaker. We've hired him before. We've attended some of his lectures that are also for the design community or municipalities. He has a wealth of knowledge and an incredible amount of experience as well. He only has roughly 60 minutes today to do his talk. So unfortunately, we can't hear all the awesome stuff he has, but please take advantage of the chat box there. Ask your questions. We'll try to get back to you kind of during the chat, but if we cannot, or Monty cannot, as he'll be chatting, we'll get back to you either as a follow-up, as we usually do through our kind of follow-up surveys, and we'll highlight some answers, and also those who can stick around a little bit after, if we need to, we can go a little bit longer and answer some of those questions live. Thanks, and off to you, Monty. We can't hear you, Monty.
Okay, now am I unmuted? Can you hear me now?
You're good. Yeah.
Yeah, great. Thank you, everybody. What a great set of informational presentations that was. I really appreciate it. I'm going to try to cover a lot in an hour, and I will stick around a little past the hour for questions, as was just mentioned. Now I have one more technical problem. There we go. As was mentioned, I work with RDH Building Science. We do enclosure consulting and facade engineering. We do energy, sustainability. Increasingly, we're helping developers with climate change planning, research forensics, and repair. Why are we here? Why do we want to talk about passive cooling today? It's fairly simple. The outdoors is hotter than it used to be for a variety of reasons. The indoor environment is hotter than it used to be, and we'll talk about why that is. And if we design buildings the way we used to, most buildings in the Fraser Valley and throughout the Lower Mainland, and indeed across much of North America, will require air conditioning now or very, very soon. However, if we design a bit differently, we can either postpone the need for air conditioning, or we can require less energy to run the air conditioning in that project, giving us a much more value proposition for the building. So what we're going to try to talk about briefly is some passive cooling strategies. We'll talk about what is overheating, what is summer comfort. I'm going to give an example of a building that's had some problems so we can look at kind of a real case study. We're going to talk about why buildings overheat, where that heat's coming from outside and inside the building so that we can think about this holistically. We're going to talk about how to use computer models to foresee summer comfort, to use your energy model as a tool for decision making to save money. We're going to talk about some design strategies for passive cooling, some mechanical strategies for passive cooling, and then kind of how to use the model to pull it all together and make better financial decisions. So buildings are overheating. It's happening across BC. It's absolutely happening in Fraser Valley and Lower Mainland. It's happening in new and old buildings, large and small. If you want to test this theory, try looking at the number of listings for small condos in Vancouver in August, and what you'll see is they drop. People who are trying to get a premium for their condo don't put it on the market in August because too many people are going to come by, realize it's really, really hot and can't cool itself, and so they sweep them off and put them back on the market in September. As an example, I'm going to use one of my own projects because I'm going to point fingers at anybody. It ought to be at myself. Harding Heights was a small apartment building in Smithers, BC, a fairly typical building for more rural communities across the province. This was built by BC Housing, who I love working with, and built for seniors. So and it was meant to be a bit of a model for seniors housing projects. It was designed to be capable of either modular or on-site construction with fairly small spaces. Again, single or coupled seniors, simple floor plans, affordable building in many ways. This one was designed for a very cold climate, Smithers, BC. This picture was taken when I was there for the mid-construction blower door test. It was literally 20 degrees below 0 Celsius. So we weren't thinking about overheating a lot. We were thinking about, can this building stay warm and comfortable with the minimum of energy in the winter? So in the summer of 2018, the mayor cut the ribbon, all these seniors moved in, everybody had lots of smiles, new building, really comfortable, really great. And then at the end of August, there was a heat wave. And some of the units, especially in the upper floors, were staying at around 30 degrees summer and winter. And many of the seniors who lived in northern BC their whole lives were used to much colder temperatures and had never been forced to kind of live in one room before. Many of them lived in houses where it was easier to step outside onto a patio or something. Were stuck with rooms that were, for them, extremely uncomfortable. It was bad enough that one tenant needed to be moved to a motel for a couple of weeks where there was air conditioning. So all of a sudden they weren't real happy with their new building. And we went to work to understand why it was overheating. There were a variety of reasons. I'll mention a few during this presentation. But it's also worth noting that in other parts of the world, 30 degrees is considered a pretty cool day. In much of the global south, many people are used to summer temperatures around 40, and 30 is like, how could people have problems at 30? And so it's worth understanding that we have different cultural expectations and physical experiences around comfort. How humid it is affects our perception of comfort dramatically. What we're wearing, of course, affects it. Our metabolic rate, the more active we are, the cooler we prefer it. If we're experiencing radiant heat coming right off a radiator or a piece of concrete or something else, airspeed affects our perception of comfort. That's why ceiling fans, for example, can make us feel more comfortable even though they don't actually change the temperature inside at all. And of course, air temperature. Now, through this presentation, we're going to talk about air temperature as a stand-in because it's sort of the simplest metric to get a sense around comfort. But before going any further, I just want to be really, really clear that air temperature alone does not fully indicate human comfort, and all of these factors matter. I'm not going to come back to that again. We could do another hour just on that topic. But because of this reason, ASHRAE describes thermal comfort as a condition of mind which expresses satisfaction. However, because we do need to put metrics on these things, they also define it as a temperature based on the outside conditions. Now, these are the acceptability limits in Smithers, that colder climate where this building was built. You'll note they're different than the temperatures that Eugene presented just briefly ago. The expectation of comfort is different in Abbotsford than it is in Smithers by about a degree or so. So not a huge difference. And as the planet warms, that ASHRAE number will continue to warm with it. Which brings us to this key point. Global warming is not evenly distributed. We are seeing global warming faster in Canada than most nations. We're seeing it faster in the north, including northern BC, than in most places. And indeed, I think we're seeing a little faster in places like Smithers than even in places like Abbotsford. It's fairly striking at the Arctic at this point, and it's unevenly distributed, even within British Columbia. And so when we looked at this building, the modeling file we used, the file that Eugene was referring to earlier, showed an average August temperature of 14.2 degrees in Smithers. In 2018, the actual average temperature was about a little more than 2 degrees warmer. And it got us wondering, was 2008 an exceptionally hot year? Was this a crazy heat wave? So we started looking back at the last decade of years before that. And indeed, they'd nearly all been well above the climate file, which causes us to ask, are the climate files we modeling to when we do these kind of modeling wrong, or are they just out of date? And it's more the latter, that they're out of date, that heating and cooling are calculated by one number a month on these simplified files, and on hourly files, they actually have much more sophisticated targets. But the number is based on, they take the last 30 years of weather and average it and even it out. So many files are based on 71 to 2000. There are newer ones, like the ones we were referring to earlier. And if your file was 71 to 2000, it's described as a typical meteorological year for 1985. Anybody want to, you can't really do it on Zoom, but in class it's fun to say, can you remember the top movie or TV show from 1985? It was quite a while ago. And the question we're getting at when we look at these files, if we're not forecasting future climate, we're designing buildings for 1985. And that is the crux of kind of how some of these issues come together. It's worth noting that buildings need to adapt to a changing climate. We've seen wildfire smoke, overheating, sea level rise, overland flooding, storms, water and electricity outages, and heat waves that can be deadly, especially to sensitive seniors. These are all described clearly as risks by British Columbia documents. And so we have to remind ourselves, who is responsible? Whose job is it to make buildings adapt for climate change? And we're not talking about mitigation, about less emissions now. We're just talking about adaptation. Legally, architects and engineers are responsible. It's not StepCode's job. It's not the Township of Langley's job. The owner may be in the way legally, and probably people will sue the owner first when they buy $1 million condo that can't stay cool in August. But ultimately, the professional accountability lies with architects and engineers. We describe this as the standard of care in practice, and both engineering guidelines and the British Columbia Building Code have made it very, very clear that all of these factors are changing and we have responsibilities around them. So let's just come back to Harding Heights for 1 minute and then we're going to move on. On this project, there was a value engineering phase, as it happens on many, many of our projects. Saved about $100,000. They eliminated operable exterior shading. They reduced the fixed shading, they cut down a tree, and they substituted one type of windows for another that changed the specifications somewhat. All of those engineering steps saved just a little more than $100,000. The people directing that value engineering were very proud of what they'd done. As soon as the building was built, it was retrofitted with air conditioning at a cost of about $2 million. I have permission to share this project from BC Housing because BC Housing has been fantastic repeatedly about sharing the lessons learned. I don't have permission to share 4 other projects we've worked on in the last several years where value engineering drove up costs in excess of $2 to $10 million because they failed to anticipate the need for cooling. And so I just urge everyone to sort of take these pieces seriously. Not understanding what's happening in our buildings will cost developers huge amounts of money and has already wound it in court actions in some cases. All right, why do buildings overheat? 6 factors. Climate change is not the only one. Outside the building, you have solar gain. How much is hitting your windows? How much is coming in? The more sun that hits the glass directly, you turn that building into a greenhouse and you start loading up with heat at the wrong time of the year. You might want a little bit of that in the middle of winter, but you definitely don't want it in the summertime. Outside the building, you have climate change happening. You also have local effects. We all know the Fraser Valley is warmer than it tends to be in Vancouver on the coast. If you are building on a site surrounded by parking lots, you're going to be warmer than a site surrounded by trees. So even your local site conditions can matter quite a bit. And that's that urban heat island effect. You need to look at your site as well as your region. Inside the building, we have occupant density, we have mechanical heat loss, and we have lifestyle variation. I'm going to talk about each 6 of these really briefly before we move on a little further. But it's important to understand that heating is coming from multiple sources, and to point everything only at one is an insufficient understanding. So what do we talk about when we talk about solar gain? Well, we've all driven past this. What is this homeowner trying to tell us when they put foil on the inside of a fairly new building of some sort? They're kind of saying, I didn't want that window, or I didn't want it there, or I wanted some kind of exterior shading. They are literally doing this to defend themselves against overheating. And if you start looking for it, you can see it in almost every neighborhood you drive around in. Most homes and apartments are overglazed in some way or another. Often meant to be sort of an architectural feature and ends up kind of having the opposite effect. What are these homeowners trying to tell us? Look at how many of those shades are drawn. And I want to say this picture was not taken on a hot day. This was taken in the springtime. So many of our overglazed apartment buildings, you see the shades drawn most of the time because people don't want that much view, that much glass, that much light. It's important to understand how solar gains work differently on different scales. Because of all of the things that produce heat in a building, on a single family home, those solar gains, especially if you're trying to build to like the Passive House or a really efficient step 5 kind of standard, solar gains can often be 70% of the gains, and the internal heat gains are relatively low in a small home. On an apartment building, it's the other way around. The internal heat gains drive the building, and you need less glazing, less solar gains, or you can never keep up with the escalating cooling load. On those single family homes, it's very important to have great shading so that the solar gains produce gain in the winter, but don't produce as much solar gain in the summertime. So temperature, We talked about this a little bit, and Adjeen had a great opening. We've seen the effects of climate change. This is a smoky sky over Vancouver a couple of years ago. We've seen how our own building code, that straight line there, is the climate change in those 2016 files in the building code are looking back at a previous climate, whereas we've seen that our actual climate has already moved past that. And depending on which path we follow, we'll move very aggressively past that by the middle of this century. We've worked to look more closely at this in the Lower Mainland and Vancouver, where many of our current past house projects are. And we're seeing that we've already surpassed predictions up to about this point. In other words, previous IPCC predictions are not quite keeping up with what we're seeing as actual heat in the climate in Vancouver. And we're seeing that peak is rising quite steeply. We're looking at July-August temperatures 4 degrees hotter than the 1970 to 2000 average by mid-century. This is not for our children or our grandchildren. This is happening within our lifetimes. So much so that when we look at a high-performance building, such as a Step 4 or a Passive House apartment building, and that's the building this was based on. This is a 6-story wood frame building in Vancouver. Notice that the heat load, the heat demand, annual heat demand drops very slightly because we don't see much loss of annual heating need, but the cooling load rises kind of quickly. By mid-century, and in fact, we're seeing it already starting to happen on this building, even though we're years away from 2050. This will be a cooling-dominated building. In other words, annually, there'll be more cooling required than heating required. We will start to think about our buildings the way people think about their buildings in, say, California, where cooling is the primary annual energy load and heating is the secondary annual energy load. Now, it's worth noting this is a high-performance building. If this were a conventional building built about 10 years ago under code, the gap between these two lines would be so high because the heat load would be so much more exaggerated. It would literally be off the charts. So they wouldn't cross in the same way, but the effect remains the same for all buildings. And so what's happening is we're looking as much as where that peak cooling load is going to be down the road as where that peak heating load is going to be. Both, do we have enough power to do that? Do we have enough cooling in the building to do that? And more importantly, what can we do design-wise to lower that peak that's coming fairly quickly? And the final outside the building factor is urban heat island or even suburban heat island. You know, what's happening on the site that might cause the heat to be greater. If you have a lot of concrete and a lot of buildings around, you're trapping the heat, especially at night when we expect that night ventilation we'll talk about to cool the building a little bit. That doesn't happen if the building's surrounded by concrete of one type or another. This is a picture of urban heat island effects in the Toronto area. You can see how large the surface temperature differences can be. I'm sorry I don't have this for the Fraser Valley right now. Clearly, if your planned project were in one of those sites, you have a very different condition, especially a nighttime condition, than you have anywhere else. And you would see similar variation across the Fraser Valley. But we model them all using the same climate tool. Our climate tool, even if you had a future climate tool, doesn't see this difference. That could be several more degrees right there. Now that works fine for winter conditions because winter conditions have that awful week in January when it's really, really cold. But they don't work well for summer conditions, and especially for summer night conditions. Okay, so we have things happening outside the building that are heating us up. Let's talk about the things happening inside the building for a minute. Number one difference is occupant density. So that little building in Smithers, and again, there's buildings like this all over the province as we move to more apartment buildings and fewer single family homes in smaller communities. That held 24 residents. It had 20 refrigerators, 20 television sets, 20 computers, about 60 meals a day, and probably about 20 showers a day. Depends on personal habits, of course. It's the same number of square feet as a big mansion somewhere in the Fraser Valley, which would have 4 residents, probably 2 refrigerators, maybe 3 televisions, 4 computers, maybe 2 meals a day are cooked in the household and served out in the community somewhere, and maybe 4 showers. So you can see the amount of internal heat gains, the amount of heat being put out in the building is very, very different as we start to live in smaller spaces, as we start to live in duplexes, fourplexes, 12-unit buildings. I mean, just it gets denser and denser and denser. And this is the other huge factor we don't often look at as clearly when we think about heat gains. Even at the same floor plate of a building, Having lots of small units as opposed to a few medium-sized units is going to change the internal heat gains quite a bit. It makes it easier to reach things like your TEDI targets, but it also increases your risk of overheating quite significantly. And then on top of that, our choices for mechanical systems can make a difference. And I can't get into this at length today, but to take one example, if you have a recirc system in your building that's flushing hot water up and down through pipes so that there's not a long time at the tap for hot water to get there, what you've basically built is a radiator, and you're running hot water through the building, heating the building up, including on the hottest day of the summer. And you're running a radiator at fairly high expense all the time so people can have quick hot water. The good news is this is one of many mechanical strategies where what you can do to reduce it also costs less to build it. If you can minimize that system, lower the pipe lengths, shrink the pipe sizes, insulate the pipe better, maybe put a pump on that slows down in the middle of the night, you can have much less radiator effect in your building. And remember that this is a particularly painful loss for the building operator. Hot water heat loss costs a building twice. Once you pay at the boiler or heat pump to create the hot water, and then you pay again at the air conditioner to cool the building because you heated it up with your hot water. So every bit of this is hitting you 2 times. And as I mentioned, the design solutions can be very affordable. This is a typical recirculation design for an older building. You had a boiler on the roof, several up and down systems to multiple units. If you switch that to a box design where everything flows past, either horizontally or vertically, past the floor and then back to the boiler or heat pump or the tank farm, you can literally install less copper pipe in your building and save energy at the same time. Okay, final factor on how buildings overheat is lifestyle variation. This one is really difficult to model, and we model in defaults, but we have to think about the possibilities. So imagine the apartment on the left. You have someone who lives a very Zen-like lifestyle, has very few appliances, they live very simply. Their entire aesthetic in life is to have a simple home. They're going to have less internal heat. And when we model with presets based on that, we see, and this is from a specific example, almost no overheating expected the middle of the summer. But if you have next door, say a couple who lives in a 2-bedroom apartment and they both love gaming, and so they've used their second bedroom to put in 5 or 6 CPUs, screens, lighting, and they spend 8 hours a day on these computers as part of their entertainment. And this is not tremendously uncommon. It's quite possible they're producing 500 to 1,000 watts of real-time heat in that bedroom, more than enough to heat their apartment and 2 or 3 apartments along the hall. They're going to have a worse overheating problem, and it's possible their neighbor on the other side of that bedroom is going to have a worse overheating problem than they were elsewhere. So our variation in internal behavior also affects how much heat gains we have. And when we're building a building and trying to create a safe environment for the next 100 years of occupants of that building, we need to make sure we've designed something that can handle either condition realistically. Because we're not going to tell people you can't play video games. If you think taking pickup trucks is hard away, try taking away people's video games. All right, so how do we process all this? And this goes back to what Ajin was talking about, the importance of a good energy model that includes looking at summer comfort or thermal comfort as part of its evaluation. The good news here is if you're doing an energy model already for code compliance or something else, you're more than half the cost there to do a thermal comfort model. The other thing I would note is on the building we showed earlier, on several other buildings several years ago, we offered to do thermal comfort evaluations for clients, and they're like, nope, we don't want to spend the money, we don't care. Later, when they write the check for $10 million to put in air conditioning, they kind of wish they had done this at the beginning, because they could have foreseen the cost, they could have managed the cost differently, or they could have taken passive measures that in some cases prevented them from having to add air conditioning. That was a great quiz. Thank you, Sarah, for putting that up earlier. The City of Vancouver and BC Housing require thermal comfort evaluation for all multifamily buildings, not for single-family buildings that do not provide mechanical cooling. To put that another way, you can put in air conditioning and avoid this requirement altogether. Or if you don't want to put in air conditioning, you have to show that the building is going to be comfortable without it. I'm not going to go into a lot of details, but as was referenced earlier, depending on the population and how sensitive the population is, for like a seniors residence where it's small and people have nowhere else to go, you have about 20 hours over those 80% comfort limits. And for a conventional population, you have about 200 hours over those comfort limits. It's a really good idea to do this modeling for any building. Not having a legal requirement to do it doesn't mean it's not a good idea. Many of our clients have been almost fall out of their chairs surprised when they saw how hot their buildings are going to be. I'm going to go through quickly some of this, but we're basically using an hourly modeling tool to simulate a single suite. It allows for us to run more variants more accurately. So we'll take a look at an apartment building. This was one of the projects we did this on. We'll pick an apartment that's relatively typical. Often we'll pick 2 worst case examples. We'll include, 4 of those sides as basically not gaining or losing heat to other buildings. We'll include some of the cooling that's already, or some of the passive cooling that's already built in, whatever the solar heat gain coefficient of the windows is, some shading that exists because there's a balcony overhead or we've installed shading devices. We'll make some assumptions for a little bit of air change that can happen through windows. You don't get a lot of air change in a unit on a double stacked corridor the way you do in a single family home or even a townhouse. And then we'll look at some variance. And so for that building, on the hottest week in August, that top line, the gray line, is what will happen by itself. And what we see, and this is midpoint of the buildings we're seeing, we see most buildings are going to do exactly what happened in that case in Smithers. They're going to hover around 30 degrees in August. Most apartments we model end up in this range. We find that if we add just exterior blinds, if we prevent the sunlight from hitting the windows, we can gain about 1 degree. In some cases, maybe 2 degrees. If we were to add tempered ventilation air, in other words, you've already got your ventilation air, it's not cooling, you're just chilling the ventilation air slightly, offering a little bit of cooling, we can usually get about 2 degrees, so give or take. If we do both exterior blinds and tempered ventilation air, we're getting down closer to 26 degrees than 30 degrees, which many clients see as comfortable, and it's starting to become within range of the comfort specs that were put on the screen earlier. In some buildings, developers can put in tempered ventilation air and exterior blinds and do not have to add full cooling. And that is a heck of a lot cheaper than full cooling. So if your only goal is to be compliant, I think you still need to worry about the durability of your building over 100 years. But if your only goal is to be compliant, and you can show that exterior blinds and tempered ventilation air will get you there, this gets you through without having to put in cooling. And of course, the final green line there shows full cooling. And in reality, the green line would be wherever you set the set point.
Hey, Monty.
Yeah.
We have a question here.
Cool.
How do you temper the ventilation air in multifamily?
Yeah.
And then someone else had the similar question. Can Monty elaborate? Or I just want to add this question. Can Monty elaborate on how the ventilation air is being tempered, please? Possibly referencing MUA. I'm not sure what MUA is.
It is going to be the last topic in this presentation, and I apologize that I am kind of racing through at the time we've got. Where you build a multi-unit building and you create a single ventilation system, not an HRV in every unit, but one for the building or one for each floor or one for each region. It depends on the geometry of the building. Often we're doing one per floor because it eliminates smoke dampers, or maybe several on the roof that are working vertically, each setting a set of suites. You can put next to the unit a heat pump cooling coil. It can also be heating coil in the winter. And that cooling coil cools the air coming out of the ventilation unit to the apartments. It's not air conditioning, because the flow of that air is maybe 80 CFM for a 2-bedroom apartment, 100 CFM for a 2-bedroom apartment. I mean, nowhere near air conditioning volume. But if you have good exterior shading, this cooling can take the edge off by a few degrees. And it hits all those units, and it's one cooling coil for many units. Both the Swigen, the Ventacity, some of the larger Mitsubishi multi-unit ERVs have this cooling coil option already built in as a packaged solution, so it's fairly simple to design. Would love to follow up with that in more length, but I'm going to leave it there for now. Okay, so we've realized this is happening. We have a sense of where the sources are coming from, and we've hired a professional modeler to build us an energy model that includes thermal comforting. And that's part of our spec at the very start. We want thermal comfort models, and we want them early in the process because we don't want to do this after we've designed the building. We want to do this before we've designed the building so we can design the building in the most cost-effective way to meet these things. What are some of the strategies that we might look at and model in and think about? And I want to just note how waiting too long kills things. So this picture on the left is from a site inspection before that building was built in Smithers, that little apartment building. Notice right in the middle, there's a big tree right there. The architect worked really hard to keep that tree in the plan. It was a mature tree. It grew leaves in the summer, causing lots of shade, and then dropped them in the winter. So the architect actually designed the building. If you look, there's sort of a dead spot in the middle there, where the tree trunks were going to be, and the tree was going to provide this great natural shading over the windows. However, this design feature, even though it drove where the building sat on the site, it drove the entire thinking for the architect who'd been really sensitive to this, it didn't make it down to the contractors who were doing the early site prep work. They looked at the plans and they said, oh, great, there's this dead spot in the middle of the site. We'll put our trailers there. So the first thing the contractor did was chop down that tree so he could put his local trailer in that particular spot where the building wasn't going to be. And of course, there's no way to regrow a 30-year-old tree quickly. So good communication is a really important part of this. What happened instead, and you can see these photos of that building, 1030, 1225, this is in August of that first year. A heck of a lot of light was hitting those windows. And it turns them into a greenhouse. You can kind of see how much light's hitting there. And of course, it got worse through the afternoon because it's a fairly high latitude. Even though the sun swings around, it stays low. So these windows were getting direct solar load about 12 hours a day. How could it not affect what happens inside the building? This was our kind of quick analysis, about 10 hours a day hitting these windows. That's a lot of solar gain on a small building. So one of the first things you can do to save money and save energy, both summer and winter, is just don't make windows bigger than they need to be. We've kind of hit this point where we do glazing in lieu of design. We just draw a glass box as our first instinct on a lot of commercial buildings and some residential buildings. We look at the building from the outside in using windows to decorate rather than thinking about, do these windows really have a purpose? I would invite every design team to just add, does this window have a daylight purpose? Does it bring daylight deep into the building? If so, it should be there. Does it have a view purpose? Is there a fantastic mountain view or pasture view or whatever? Then the window should be there. Does it have a ventilation purpose? Is opening this window in concert with opening another window on the other side of the house create great cross ventilation? Absolutely, there should be an open window there. If it's not immediately obvious that a window has one of these three purposes or some other purpose, take it out. It'll save you money in construction. It'll save you money in the winter because you don't have to heat as much, and it'll save you a lot of money in the summer. So more than anything else, just getting windows to have a strategic purpose. I am not saying take windows out of the buildings. I'm not saying dark windows. Buildings should still have lots of glazing in the right places. Just be strategic about where it goes. Second passive cooling measure, specify low solar heat gain coefficient. I won't go into this at great length, but these are basically a function of the coatings we put on the inside of double or triple pane glass that cause less solar light to pass through while you still have great vision running through. And they can lower the solar transmission of the glass down to the 10 or 20%. 30% is pretty typical. 40% is kind of high. 50% is really high. One of the main things that happened on that Smithers project was that the revised windows, which cost less, had no coatings. And so the solar heat gain coefficient shot from what was specified down around 25%, give or take, to up at about 50%, causing a heck of a lot more greenhouse effect in that building. So one of the easiest things to do is tweak the solar heat gain coefficient. And I'll tell you, this is where you really want to work in close concert with your energy modeler, no matter what type of energy model or energy advisor you're using, because you may say, do we want to crank this up or down? And it has effects in winter, and then you get a little less heat in. But if you're counting all your internal heat gains, maybe you don't need that heat in winter, and it has effect in summer in solar heat gain. So you're effectively adjusting this like a dial to understand what's happening in the project.
Hey, Monty.
Yeah.
I have a comment that has come up that maybe you can comment on their comment. So from Corey, he said, bigger windows and better views attract buyers, but after they've lived there a while, they close the blinds, as was mentioned. The point is making windows smaller is a barrier to selling homes.
I wish we had another hour to talk about that.
Yeah.
I agree that that is said by many realtor marketers. I don't believe the data backs it up. We see some of the new townhouse and condo projects here that are pursuing more traditional designs and have smaller windows, or we see heritage buildings with smaller windows selling for the same or more as other new product. So I think that's definitely a meme in our real estate culture right now, no question. Does the data fully back it up? I'm not certain, but I'd love to have that conversation based on data at some future point. But I understand where it comes from.
Great. Then we have one more potentially quick question from Mohammed. What glazing percentage do you recommend?
For the residential portions of a multi-unit building, we would try to look at 30 to 40%, understanding that the higher you make it, the more it's going to cost you, both in glazing and other compensating factors. We are currently working on a project downtown Vancouver that's a 60-story passhouse tower that is about 40% glazing. I would challenge anybody standing in any of those units to not think of them as highly glazed to the outside. The building looks to be more glazed because the cladding is also glass that's tinted to match the other glazing. It may be the world's first faux curtain wall building, but it's actually about 40% glazing. Now, that said, the ground floor lobby is 80% glazing. There's a huge amounts of transparency because you want to be able to see in, see out in other pieces. The ends of the hallways have more glazing. So there's places where there's more. Affordable housing projects, we tend to push it down to more like 30% because it just saves so much money through the whole process that can go to more floor space, more space for people to live in. It's also not uncommon for office buildings or commercial buildings to have portions that are much higher because they want to have one really impressive entryway or meeting room or something like that. So again, it's all about being strategic.
Great, Monty, thanks.
Okay, so we all know the sun comes to us in different ways during the day from different places. It rises fairly high to the south and it's fairly low to the east and west as we move through the day. And so when we think about fixed shading, how we're going to keep sunlight from hitting the window, you need to think about the direction foremost. To the south, having a shelf above the window, if the window is not full depth, can be very effective. If the window is full depth, like a glass door, that shelf has to be huge, more than 8 feet in our elevation. To the east and west, putting shading along the sides of the window or the sides and top in combination is more required because the sun's lower. It has a different effect there. Our worst overheating tends to be from the west here in this part of British Columbia. And then to the north, there's not a heck of a lot of reason to have shading on, although some can help you with the light that sneaks around to the east or west. So realize that one's shading strategy changes as you work around the building. It's not the same as you come all the way. This gives a nice example of how south-facing shading for full-depth residences, these are floor-to-ceiling triple-pane windows in this building, can work in winter. At winter time, the sun comes and nearly covers that window, which is what you're aiming for. But at summer, it's much higher and it actually is fully shaded. Unfortunately, I wasn't there to take another picture in the summertime. But also notice how deep they are. When you stand on the street, you can't even see the windows. In order to have real protection for full floor-to-ceiling windows, your balconies need to be very, very, very deep. And some municipalities, not pointing any fingers here, tend to limit balcony depth because they charge you as the balcony gets deeper, and so this becomes a real challenge to do. And here's an example of that west-facing shading in an office building. So different context, I understand we haven't done anything quite, this is in Brussels, we haven't done anything quite like this in Vancouver, but great shading all the way up the building, significantly reducing the cooling load on this office project. This is a good example from a community near here of how not to do shading. See those little light shelves that are installed that just shade the building? They don't even touch the glass, I see this all the time. People have just put on shading devices in a way that they're not going to be effective at all. To take those same things and put them down on that second story from the top where the windows are full in sun could have been kind of useful. As it is, these are just decorative elements. They serve no shading piece. except perhaps to remind us that shading needs to be strategic. It's a functional part of the building, not something that's bolted on afterwards. And finally, the pattern that really works is as we think about our climate becoming more like a Mediterranean climate, and that's sort of the good news about climate change for our part of the world. If you look at, there's many parts of the global south that are going to be far less habitable by the end of this century. We remain very habitable for most of the time. We will have problems with population pressure and forest fire smoke and other questions, absolutely. But we sort of become a Mediterranean climate, and it would make sense for us to start looking at how people design buildings in Mediterranean climates and thinking about that as we look towards 2100. The number one pattern is a brise soleil. It's an ancient pattern. It's been all over the world. And as the South comes to us, we can import some of that here. Brise soleil doesn't have to look Mediterranean. I mean, this is a project where there is simple shading on all of these south-facing windows that allow the light to be knocked down. And in this case, the view was not great to that particular direction. It's of a train station and a busy street, and the apartments face the other way, back to the courtyard. And so it has this great possibility of great shading, interesting architectural design, with still a lot of light in those hallways. There's another example. This is a project Past House project in Australia. It's a dormitory project. You really see the brise soleil. You don't even realize what the building is behind it. The brise soleil becomes the defining feature and basically shades the project with fixed shading to radically lower the cooling load in a community right near Melbourne. Sometimes it's horizontal, sometimes it's fixed. There's lots of different ways brise soleil and shading can work, but as a pattern, as something to think about, I urge people to work with the architectural teams to think about where it makes sense. And then finally, let's talk about operable exterior shading. What we've been talking about so far is fixed. It's mounted on the building in some capacity, and it stays that way for the life of the building. As we noted, the sun moves through the day, the path changes through the year. And so fixed shading is a little bit like a broken clock, not so much the brise soleil, but the above and light shelf shading and side shading. It succeeds twice every 24-hour period. The rest of the time, it's too much or too little, just as the sun's moving around. If you have the ability to adjust your exterior shading, your passive cooling strategy is much more robust. You don't literally need to adjust it all the time during the day, but you're kind of adjusting your exterior shades a bit for May, again a bit for June, again a bit for July. Where it's operable, you get real savings. And you really see it on a single family house more than on a multi-unit building. But if you create a single family house and you're trying to hit step 5 or passive house, if you have a lot of glass to the south and west, you open up that shading. In the wintertime, you get the solar gains, even on a cloudy day, and you heat the house. In the summertime, you have all this exterior shading that comes back down over those areas that can be simple or complex. On some buildings, simply that ability to manage your solar heat gains more effectively can result, if you are trying to hit those higher step codes, in 2 to 4 inches less insulation around the building. So you're spending the money on operable shades and on strategic glazing instead of just lots and lots and lots of insulation. So let's just talk about why outside the glazing, because we've all seen shading inside, as you can see kind of behind me here on these walls and others. We've all seen level shades. So just imagine, you've got Mr. Sun out there, and you've got a triple pane window, and you've got the person you're trying to keep comfortable inside the building. If you put the shades inside the glass, and you start with about 100% of the solar energy coming through, and this is setting aside solar heat gain coefficient or other factors that might be effective, about 75% of that heat is going to get into the building, in most cases. Every building is going to be a little bit different, and so I recognize this is a sort of generic case, although it comes from some DIN modeling standards that are used regularly. So putting the blinds inside will knock back some of the heat, but very, very, very little. However, if you put that same set of blinds outside the window instead of inside the window, you knock out 90% of the heat and only 10% passes through. And remember, you still have the ability to just raise them out of the way in the winter when you want to let it through. It's a difference that's almost an order of magnitude. And when we model it, it's significant. The nothing but nothing gives you better passive cooling performance advantage than putting shading outside the window that you can move. That's why you see ancient houses. If you look to China and India places, it's not uncommon to see sort of reed mats or things outside the windows hanging from the eaves in some capacity. And just to kind of wake our brains up, let's quickly look at 10 types of exterior shading. just to see what we're talking about here. So it could be as simple as cloth outside the window. It could be as simple as a cloth awning that raises in a more sophisticated design way. This is a cloth awning that pulls up in the summer and drops down in the winter on a project. It could be the sort of articulated awnings we see all across the global south in cities and communities, just great exterior shading devices. It could be roller blinds that pull down both for security reasons as well as for shading protection. They're simple devices. They're made all over the world. They can be part of a very architectural expression. They can have different degrees of light passing through them, different degrees of transparency or privacy. It could be Venetian blinds. These are Venetian blinds in Venice. Notice they're put outside the building. These are the same $10 blinds we buy at the local hardware store. It's just there they put them on the outside. Do they rust and weather? Yes, but they only cost $10 in the first place, so you just replace them every 5 years and put on a second one. This is how most of Venice does their windows, and many other Italian communities. You can also buy for much more money, much more robust exterior blinds that are built with tough aluminum materials, tough wires, tracks they can run up and down on. They will flex in the wind. They will handle the snow load. Obviously, they're more expensive than the $10 version you buy at Home Hardware. Some blinds can be controlled from the inside. So these ones tend to be controlled, by the way, electronically. There'll be some sort of device inside that will either sense sun hitting the window or have the ability to just override the blind. These simply have a rod that goes through. So this is on an apartment building project. The blinds are on the outside. There's a rod from the inside. They literally replace simple blinds inside the apartment. This is another school project, blinds outside. This is an office building project, blinds outside, giving the ability to both open the windows and prevent direct glare in the building really simply. This building is interesting that actually has blinds on both sides. You have blinds on the outside for solar gain protection and blinds on the inside for privacy and to change the quality of light somewhat in the same space. In several parts of Switzerland, it is illegal to install air conditioning until you have already put on exterior blinds. And this is from one of those communities where you'll see even really small buildings in snowy communities. This is a ski town. Have exterior blinds because if they want AC, they have to have the blinds on first. That's how important it is. Rolled screens are another option. These are available widely here. They just run in a track. There's a little motor and a wire. You've got some buttons on the wall. You kind of put them up and down, and as you push the buttons, these screens come down, protecting the window from the outside. You get the idea there. If you want to spend a little more and you want that clean international style to the building, you can get blinds that are integrated into a window unit. So what you're seeing here is a triple pane window, and then there's about a 1.5 inch gap. In that outer gap between a fourth piece of glass, which is ventilated the outside, there are blinds that rise up and down. There's a schematic view of this window. The major window makers all make a product like this. It's not cheap. I will be really clear about that, but it gives you the ability to put blinds outside the glass, inside the window. This has become the kind of go-to solution for most office projects and projects of that type in Northern Europe at this point. And you can get a full door like this with the blinds installed behind that fourth piece of glass. Shutters and French doors are also ancient solutions. We've looked at these across the world for many, many years, realized that whether everybody's remembered this or not, these are primarily solar shading devices. That's why we put shutters out there. There is a feature of security and other features, but the reason many, many buildings around the world have shutters on them is because it's one of the cheapest and most durable ways to create operable exterior shading. They can be very modern. They can harden the building by being metal. They can soften a building by being wood on top of an otherwise concrete or stucco project. They can they can be very modern. They have lots of ways they can look, but shutters and French doors remain really popular. Sliding panels might be one of the most affordable and easy to build pieces. This is a small passive house residential project in Seattle that built these exterior shutters. Now note that this is the west side of the building, so you can reach out your window and slide those to wherever you want them to minimize the heat gain there. This is what it looks like from the inside. You can push them all aside, and you might do that for much of the winter, or you can close them all over, and you might do that for much of the summertime. But really easy, simple to build. And note Again, we need different strategies for different sides. So that's the west side of the building on the left where you saw the movable shutters, but the south side of the building on the right in this image shows the light shelves above because ice south, sun in the needs a different strategy, right? So again, look, a different strategy for each direction of the project. Sliding shutters come in all sizes, are great on single family, townhome, large building, but they have to be part of the design. They look awful if you try to retrofit them. So if you're not having this discussion with the architect, in fact, if it hasn't been written into what you're hiring your architect with in your owner's statement of requirements that I want exterior shading that's affordable and durable, you're probably hiring the wrong architect. And if your architect doesn't have experience doing this, they're not tremendously well prepared for the next century. And by this, I mean all of these patterns, not necessarily this one. Moving louvers are a more expensive way, but one that can save a lot of money. So this is a high school near Leipzig in Germany. All of those green shutters shift every hour over, and the program for where they shift changes during the year, letting in the optimum amount of light for that particular day. And the program actually changes slightly on a cloudy day than a summer day, or than a sunny day there. But it allows every classroom to have great light, the appropriate amount of solar heat gain, but not too much solar heat gain. And here's the interesting bit. If they decide maybe that the solar heat gain adjustment was wrong, that maybe it's a computer lab or things are happening inside that are producing more heat gains, they can adjust the program and keep tweaking this over time. This is a strategy that can actually change with the climate to some degree. The architects on this project estimated that the exterior blinds allowed them to remove 3 inches of insulation from the high school. So that trade-off of gains is there. And again, your trade-offs will be different, but you don't know what your trade-offs are unless you're having a conversation with your energy modeler at the beginning of your design, it's schematic design. It's not something you can retrofit. Well, you can, but it's really expensive. Remember too, the shading can be outside the balcony too. It doesn't always have to be right in front of the window. It's usually most durable right in front of the window. This is a project in Vancouver. This is facing south. And the shading is out at the edge of the balcony. So it creates a private space, a space where people can sit out and have breakfast and feel less seen by the world, which some residents might want. Here's another project with shading out on the edge of the balcony space. I would note, by the way, if you look at this building, and this is in Berlin, they have all of the strategies going somewhere here. They have movable shading at the edge of the balcony. They have shading of a pull-down type right in front of the windows, those white fountains, and they have awnings at the upper level. And I think this is what you see when you have architects and teams that have been working with us for years. There's no one-size-fits-all solution, but you work from this palette of shading devices according to where you are in the building, what style your building is, what your price ranges are, and you kind of get better at it as you work along. This is shading on a single-family project. Really nice edge of the balcony shading, all made in wood in a wood region of the world. This is actually an extension to a traditional house in Switzerland. The entire project, both the traditional house and the new house, are built to the Passivhaus standard. But this great example of wood shading, especially in a community where we're trying to do more with wood and letting wood be wood, letting it age on projects, is a kind of elegant way to go about this sort of thing. And then finally, we haven't seen this a whole lot yet, but electrochromatic glass is coming into the market. This is glass that takes a slight charge and changes its tinting fairly dramatically. We've had projects that have looked at it in downtown Vancouver. Nobody's pulled the trigger on it yet. It's very expensive and there are some durability questions. It's gained an initial market foothold in retrofits of highly, highly glazed buildings in places like LA and Texas, particularly like airports and office buildings. It is, for them, cheaper to replace all the glazing with this than it is to do exterior shading on some of those projects. Okay, my point here is simple. Don't tell me you can't do this. There are at least 10 patterns of operable exterior shading. We have kind of run through them fast. You could probably find 5 or 8 more if you think about it, but have this conversation with architects and designers right at the beginning, because it is an affordable way to reduce the solar gain portion of overheating. Okay, I'm going to race quickly here because we're nearly at the end of our time. There are also some mechanical strategies you can look at a little bit. You can use ventilation to cool the building at night. Do the physical strategies, design strategies first, the mechanical strategies second, and then if you need cooling, that's your full air conditioning. I mean, that's your source of last resort. Night ventilation is how we've done things here in the Lower Mainland and the Fraser Valley for hundreds of years. Basically, we open up the windows and doors at night, air flows through. In most single-family homes, you've got some greenery around you, and you cool the house at night. It kind of stays just cool enough through the day. It's a little hot in the afternoon, but you know evening's coming, so you're not worried about it so much. And in many single-family homes, so what if the house is a little warm right before sunset? You can move out to the garden and sit out in the garden and have dinner and enjoy your time there. That's not the same option if you have an apartment building on a double-stack corridor. We never have a through flow of air. And it's not the same option if you have an apartment building without a yard where you can go retreat to when it gets really hot. But this cross-row ventilation is why we're seeing overheating manifest itself more severely first in dense apartment buildings, but that's not saying the same issues aren't happening to a lesser degree in Part 9 construction. Most of you know what heat recovery or energy recovery ventilation is. It's pretty much required by the STEP code. I would ask that it is extremely cost effective. We find in our large projects, the more efficient our energy recovery ventilation is, the more money we save on everything else. And I'm currently working on an extreme example of this I want to mention, where we're Pass House consultants for the new Vancouver Art Gallery. Very, very, very large building, very high design building, lots of design requirements brought in by the architects in the art gallery. To go from a 75% to an 80% efficiency ERV on that building is $1.5 million. It's a major difference, but it saves more than $30 million in additional insulation and other construction measures. And so spending more on the ERV is saving them, $18 million or something like that. Now, that's an extreme case. Most single-family homes, you're never going to see that same range, but the same principles apply. You can almost never go wrong spending more on your ERV. Now, a high-quality ERV, not the cheapest ones on the market, also can cool at night because they run on bypass. They just take the night air, they go around the cooling coil through another little channel and go straight in. And so they're doing the same thing that cross-flow window ventilation was doing. They're bringing cool air at night into the building, cooling the whole building down, except they do it more reliably, and they can do it even in an apartment building where you might not have, or some townhouses where you might not have great cross-flow ventilation. It's essentially free cooling. And with the combination of a little bit of solar shading to prevent you from overheating too much in the afternoons and free cooling at night, many of our homes are going to be fine when we run these models for another decade or two. Like you buy a full cycle where the point at which they might need cooling will be closer to 2040, 2050. And so you can create a building that'll leave lower cooling load then, but you don't have to put in air conditioning now. Balanced ventilation can do something else too that the windows can't do. It can filter out the smoke. We've seen what the wildfire smoke is like. We lived with the last few years. Our foresters tell us we have another 20 plus years of fire, dead wood lying in the forest that is going to burn. Our HRVs have filters in them, our ERVs. And so when we bring in night ventilation through the ERV, we also filter it. We have the possibility when our skies are full of smoke, we can just change those filters every couple of days. And all of that black stuff you see, that one on the left was right after a couple of days of wildfire smoke. The one on the right was prior, a normal dirty filter, if you want to talk about it that way. That's all in the filter rather than in the lungs of the residents. And again, you can't do this with windows to the same degree you can do it with an ERV, so it's a great system. And then finally, to the question that was raised earlier, thank you, you can deliver mild cooling in the larger units where the air is cooled, it runs through a coil near the ERV when you have a central. This would be ridiculously expensive on an apartment building with lots of small units. You could do it in a single family with the higher end units, like Zender has the cooling coils you can run on their units, and in apartment buildings you can do it. It's not air conditioning, but it's what we're finding, this plus good exterior shading together can evade the need for full air conditioning in our larger projects. Just to mention, the first building in BC that's actually installed this, and I'm aware of time, by the way, Sarah, I'm almost there. Can I have like 4 more minutes? Okay. Whistler Housing built Past House workers housing in Whistler, and it's one of the first projects to use that tempered air cooling. It also provides tempered air heating through the whole system. It was less expensive with the central ERV and the cooling than it was to put in 24 local ERVs, one in each unit. So less construction cost. Easier to change the filters because you have a central system rather than you have to enter each unit to change all of those filters, and the ability to add heating, cooling, and in muggier climates, we also can add dehumidification, which is a major issue, not so much in Whistler. These have custom dampers that allow the residents to control the flow within a certain degree, and thus it's not exactly a thermostat, but it can give them more or less cooling air at different times of the year in a system like that. And I just want to come back to this point, you know, good ERVs or HRVs at a residential scale, they're large. The one on the left there is a Zender unit for a 2-bedroom house or townhouse. The one on the right is the size of a Zender for like a 4-bedroom house. So, I mean, they're the size of a refrigerator. You have to plan the space in, and where it goes matters. They cost more than a cheap unit you put up above the bathroom ceiling somewhere, but they deliver all of these benefits that if you really cost them out will cost you less than the alternative and create a far more durable place. And then finally, if you do have to go to cooling, if you need full air conditioning, realize that if you set up a heat pump system for the whole place, you get the heating and the air conditioning at a high efficiency in one. If you get pushed to air conditioning, the first thing you do is you yank out the gas line, because you don't need a boiler, you don't need a furnace anymore at that point. You're going to put it in the heat pump for air conditioning, and therefore you have it for cooling as well. You don't want to pay for two systems. I'm going to have this gas system that's do the heating and this heat pump system that's do the cooling. Do it once with a great multi-split heat pump, and you're done. Okay, quickly, how do we put this all together? This is a bit of a recap. Understand all these factors. Climate change is a factor, but it's not the only thing that's heating up our buildings. Our design and our density and these other factors are very real. 2, identify appropriate strategies, the kind of things we've talked about throughout this presentation. 3, ask your energy modeler, the person doing your crumple analysis, to include your strategies. If you want these strategies and they haven't modeled those, your model didn't give you what you need for. You're the client, you're paying for the model. You need to specify what you want modeled, so that you can say, I want to look at exterior blinds. I want to look at tempered ventilation. I want to look at the combination of that and other pieces. And then use that information to make decisions. Now, I wish we had done this before we did the Smithers building. But BC Housing, who I have lots of good things to say about, did pay us to go back and look at the building and model it extensively after the overheating problem. And so this is what our options would have been there if we had looked at this before. And if we'd had this information before design, I don't think we would have gotten the problem we got. It's a lot on this chart, but if you look here at this sort of darker red line, this is the 200-hour limit, and this is the 20-hour limit that would have applied to that building. We can see that, you know, with no natural ventilation, with those things, it gets really expensive fast. That low E coating alone wouldn't have worked there. That, you know, some operable or fixed shading, depending on how it worked, alone wouldn't have worked there. That increasing natural ventilation, because you have much cooler nights there, would have got you to the 200-hour limit, but not the 20-hour limit. But here's where it gets interesting. Some of these bundles did get you there. Operable exterior shading plus low solar heat gain coefficient glass, which I would have is what we originally specified, would have kept the building cool. Adding a cooling coil to the HRV would have kept the building cool. Doing both of those things would have dropped you to complete cool. So there was no reason to add air conditioning to this building, ever. And yet, because it was designed poorly and created a hot box that had to be cooled, air conditioning was added at very high expense. That's why I use this as example one, because it's kind of my fault and the teams I was working on fault. We built this, so I'm pointing my fingers at myself and people I've worked with again and like working with. But it's a classic example of where if we had had this information clearly presented at the beginning of design and not value engineered out, we would have saved millions of dollars. Sorry. Okay, so summary, the outdoors is getting hotter, indoors are getting hotter. Our community needs buildings that'll keep us safe for the next 100 years. Forget about step code for a minute. That's just what we need to survive. And we, architects and engineers, are legally responsible for these things happening. The step code is a great starting point. Understand that the real constraints are not the step code, it's adaptation and mitigation, survival in buildings for the next 100 years in our climate. We're going to have to go beyond step code of some of these issues. Sorry to run a little bit over. Thank you very much. If you have to go, totally hear you. I will stick around for a little bit to do some more questions here if people want to.
Great, thanks, Monty. That was very good. We have 2 questions in the queue right now. one from a bit earlier on, but it wasn't really specific to what you were talking about. So from Wally, we have solar panels can create shade. Can that be part of the modeling?
Sure. I mean, you can build a shade device out of anything you want, and solar panels are an interesting option. There's an interesting passive house project in Philadelphia that wrapped all sides of the building. It didn't use cladding, basically used solar panels on the roof and around all the sides as a kind of bris de soleil. The solar panels are about a foot away from the cladding itself, and so they cool the entire building. And they generate enough power that that multi-unit building is net positive. It produces more energy than it uses in the years. So yeah, I think they're a great option. The other thing I would say is that in some buildings, using solar panels as part of your decorative strategy really works, and you have clients who really want that. In other times, you have clients who want a really traditional look, and they would rather have solar all over the parkade, over the garage, or somewhere else. So it's a design question. What else do we have?
Thank you. Another question from Donald. Question for Monty. You can get to it. If you remove the gas in a building after installing heat pumps, what do you suggest as backup for the heating portion of the system if the heat pump cannot operate during cold outdoor conditions?
Yeah, that's a great question. That's a question that gets to the heart of the biggest design debate we're going to have for the next decade. Do we just fully electrify with buildings as we have, or do we increase the thermal resistance of the building, building a step 4, step 5 kind of building where your heat peak load has dropped so much more that you have more resiliency built into the building? I think for most climate zones, it makes sense to do both. And so if you're doing a new building at step 4 or step 5, it is much easier to electrify, and your risk of a power out or something like that is much lower because the building will stay comfortable for a day or two. Whereas an old 2x4 frame house, poorly insulated, we've all seen gets cold after 8 hours. In places like California, where we're also doing some work, it may make sense just to go to heat pumps now. Your risk of winter is less. That said, as backup in the interim, there's nothing wrong with some electric resistance as a backup. And several of our projects, we have electric resistance water heaters and other pieces that can provide that backup without needing the extra gas. But if you build it into the enclosure, it costs less than sort of the extra backup system. That said, I want to be clear, you do have to model this for every building. Don't take one thing you heard on a webinar and decide that's your building strategy. You want to model it, look at it, talk to your engineers, consultants on every project.
That's fine. Yeah, that's very true. And we have one more question in the queue from Bing Hang. What is the typical air changes that natural ventilation can achieve in a MERV?
Wow. You know, we spent a lot of time modeling and debating that, actually. And it's probably like, if you want to just watch my team I work with at RDH in our bullpen, like lose focus for an hour, ask that question and watch everyone debate for the next 45 minutes. It's very low. If you have a double stacked corridor, you only have windows on one side, and you might also have window limiters. Like the picture on screen right now, the window opens all the way, but as we know, many apartments, especially apartments built to BC housing guidelines, have limiters that only open 6 or 9 inches, right? So you have no cross ventilation and limited window openings. The natural air change rate, 0.1, 0.3, 0.5 air changes per hour maximum. It's so low, it almost doesn't matter, which is why you really need that night flush through your mechanical system. We don't see it as meaningful. Now, if you have a townhouse near the water where you have great cross ventilation and the windows are not limited, you can open them up all the way. Or you can get great stack effect. You can, on the 3rd floor, open up windows a lot and then maybe have some windows with some guards down low that are open. You can change that, but you do need to think about how your natural flow works. And it's the reason why MERVs are the worst, because they don't have the same kind of cross ventilation. It's a really good question.
Thank you. And then we have one more question that's come in from Jason. I think this is probably more of a question for the township. So will code eventually mandate passive cooling / future climate analysis? So I'll give you the floor, Monty, and then if we want to add anything, Kevin, we can pop in.
Yes, I think it will. I mean, what we've seen for years is these things tend to start with places like the city of Vancouver and BC Housing, And what happens is we work with them in Vancouver for a few years and we work out the bugs, and we find that some ways of implementing code are not as good as others. I mean, Vancouver's always been kind of a laboratory for these things, but we've seen for many, many years ideas that kind of get worked out in Vancouver. We learn from our mistakes in Vancouver, and then they get picked up by code in BC. And then years later, they get picked up in code in other provinces. So I would anticipate this will go through that pattern. But given the liability that developers face, especially as our housing prices are getting so high, if you pay $500,000 for a condo and it's uncomfortably hot in August, you might not feel great about the person who sold you that condo. And so I think given the liability that risk doing these for a model that's maybe, depends on your consultant, but maybe $10,000 to model those 2 units and give you all those variables and consult back and forth repeated times on that. And that's what you're going to pay my team to do it. You can probably find somebody who does it for less. That's $10,000 that could save you hundreds of thousands or millions. I wouldn't wait for code.
Great.
I'll just jump in here as well, just to note, to comment on Monty's response. Yeah, I don't know when or how it'll be implemented, but I can tell the folks on the call that it's being examined from many different groups to address this. So don't be surprised if in some kind of near or long-term future or very near future that this starts to show up in different municipalities and eventually the province and federal government. This is, you know, as Monty has very clearly highlighted, it's something that's very aware to us. We're very aware of it, and steps will be taken soon.
Great. That's the end of our questions. So I guess
Great.
Kevin,
We can start wrapping it up. So yeah, it's thanks for those who are still on the phone. I really, really appreciate it. So we'll take some steps to wrap things up. Credits, it's in front of you. If you have any questions, please reach out. I want to highlight Sarah put a link in the chat, and she will follow up with everybody who's attended today with a link to a survey. We do this every single time. Please do the survey. This is how we develop our programs and gather feedback from you and have that really dialogue outside of the chat box. So I very much appreciate you doing that. Monty had a lot to say today. It was awesome. I want to highlight as well, Sarah did note that we do keep all of our webinars on our website. Email us if you don't know how to find it, but we do have all these recorded. You can come back and watch it whenever you like to recap. There's so much good stuff, and I don't want to kind of summarize all these amazing things into one little piece, but at least one of the take homes I have here, which really makes things kind of simple from a dollars to cents. I'm a dollars to cents personally sometimes, and it's kind of a question or comment to Monty and the gang. It's that if we hire a modeler at the outset or at the concept stage and work with them to turn the dials, what I've learned here today is that I can save up to, you know, thousands, hundreds of thousands, if not millions of dollars in mechanical systems by addressing cooling from a design perspective. This is, I think, one of the take homes I've gotten from this, and I'm hoping some others have gotten that as well. That's a pretty heavy hitting concept amongst many others there. So that I thought that was really great, and thanks, Monty, for giving us so many examples of that. And a few other kind of pieces here. So thanks again. You know, it's do we want to put in mechanical cooling or not? I think if you choose not to, at least with some of the tricks we learned today, you will have an easier time achieving that. Yeah, I think I'll wrap things up right there. So a big thank you to again Monty Paulson from RDH. This was great. I think we all learned a lot, and via a lot of the comments in the chat there, I think the gang really enjoyed this. Thanks to BC Hydro for your ongoing support. Big thank you to everybody here in the room for attending. Ongoing this community we developed with you, and this partnership has been really awesome. Again, this dialogue is really great from the feedback and from the chat. And as well, we want to say thanks to somebody you probably come to know over the last year and a half, and that's Sarah. Sarah, unfortunate for us, but fortunate for the community at large. She's moving on to another internal department, our sustainability group, who you're probably aware of as well. She'll be taking on a more senior role there. So thank you, Sarah, for everything you've given to the Build Inform series. It was a great, you've done great things for us. So thank you for that. We will for sure carry on the program in some way, shape, or form. We'll just, Jean and I will have to kind of muscle up a little bit. Again, thanks again. We are meeting in September. You'll have some communications from us before then regarding, again, that survey that on airtight buildings and where you come in from a construction aspect. That's a big project for us. So we really hope that you will participate in it. And for any questions we hadn't got to in the chat, we will have a follow-up. And Monty has, I believe in his presentation, he'll have his email address. So if you do want to follow up with him or reach out to him and his group for design consulting, I'm sure he'd be happy to accommodate. Okay, that all being said, thanks everybody again for attending. Really appreciate it. We'll see you in September.
Have a great summer.
Thank you.